Hi, everybody. It's Professor Mitchell. Today, we're going to start talking about confidence intervals, starting with confidence intervals for a population mean. And here we have a copyright notice, which I will skip over. You can pause and read this if you're interested. Okay. So again, confidence intervals for population mean. Here are some of the objectives. Find and interpret confidence interval estimates in business examples using the empirical rule. Work backwards to calculate the error bound and sample mean given the confidence interval in business contexts. Determine the z-score for a stated confidence level and compute the error bound in business applications. Calculate and interpret the confidence interval for a population mean with a known standard deviation in business examples. And then finally, find the sample size required to estimate a population mean with a given confidence level in business applications. So before we get into this, the idea behind a confidence interval is that you're trying to estimate the population mean, all right? And later we'll talk about estimating a population proportion. So you want to estimate the population mean, and the best way to do that is to collect a sample and calculate the mean of that sample. Now, because you're only working with a sample and not the whole population, there's going to be some error in your estimate. So what we're looking at here is the what a confidence interval looks like. So you have point estimate, and in this case, point has to be your sample mean, all right? That sample mean is going to be right in the middle of the confidence interval, and then you're going to calculate a margin of error, which your book calls EBM, and I think I figured out that stands for error bound margin. All right, so and then you can say something like, we are 95% confident that the interval from, let's say, 40 to 50 contains the true population mean. All right, so I think we talked about the empirical rule previously. The empirical rule says that when you have a normal distribution, approximately 68% of the data lies within one standard deviation of the mean. 95% of the data is within two standard deviations of the mean, and 99.7% of the data is within three standard deviations of the mean. So this concept is very closely related to the concept of a confidence interval. Okay, so here's a simple example to get started with. The population mean of a set of data is unknown. However, the sample mean is 6, and the error bound for the mean, maybe that's what EBM stands for. The error bound for the mean is 3.0 at a 95% confidence level. Find and interpret the confidence interval estimate. So this is a really, really simple example. You usually won't be given the error bound for the mean. Normally we're going to have to calculate that, so that's going to come later. In the meantime, once you have the sample mean and you have the error bound for the mean, you just add and subtract that error bound to the mean. So remember earlier, the format of a confidence interval is x bar minus the error bound up to x bar plus the error bound. So in this case, that would be 6 minus 3 up to 6 plus 3. So it's the interval from 3 to 9. This is interval notation, all right? So it's all real numbers between 3 and 9. So the interpretation is, with 95% confidence, the population mean of this set of data lies between 3.0 and 9.0. All right, here's another example, very similar to the last one. This is one that you could try if you'd like to pause the video and try this one. The population mean of a set of data is unknown. The sample mean is 6.2, and the error bound for the mean is 2.7 at a 68% confidence level. So X bar is 6.2 and the error bound is 2.7. Find and interpret the confidence interval estimate. So again, you just add and subtract that error bound from the mean. Please note that when you write interval notation, you should write the smaller number first. So the subtraction always goes first because that's always going to give you the smaller number. So 6.2 minus 2.7 is 3.5. 6.2 plus 2.7 is 8.9. So with 68% confidence, the population mean of this set of data lies between 3.5 and 8.9. All right, so now we get into how to find this error bound for the mean. If we know the sample mean, then subtract the sample mean from the upper value of the confidence interval. So this is when you're given the confidence interval. This is another pretty easy thing. What we're working our way up to is actually calculating all of this stuff from scratch. So if you're given the confidence interval, then all you have to do is subtract sample mean from the upper value of the confidence interval. If you don't know the sample mean, then subtract the lower value from the upper value and divide the difference by 2. And that will probably make a little more sense when we look at an example. Okay. Oh, and then to find the sample mean, yeah, because we were just finding the error bound. To find the sample mean, if you know the error bound, then subtract the error bound from the upper value of the confidence interval. Remember, in the previous examples, we found the upper value of the confidence interval by adding the sample mean plus the error bound. So this is just doing it backwards. If you don't know the error bound, then take the average of the upper and lower values of the confidence interval. Okay, so here's an example. Given the confidence interval 18.2 to 26.8, find X bar and the error bound for the mean. Okay, so remember that the sample mean is right in the center of this interval. That's why to find the sample mean, we take the average of the upper and lower limits. Okay. So when you take the average of the upper and lower limits, in this case, you get 22.5, okay? And then the error bound margin, the error bound for the mean is the distance from the center of the interval to either of the limits, either the upper or the lower limit. So what they suggest is that you take the upper limit and subtract the sample mean, okay? So in this case, the error bound for the mean is 4.3. So I just want to point out, let's see, I think I'll have to do this with my pen. The way that I normally like to write confidence intervals, well, really I like to write them using interval notation, but before I write them using interval notation, I will often write them like this, 22.5 plus or minus, whoops, the error bound, which is 4.3, okay? All right, so in this case, we were given the confidence interval, but you can use this to verify that the answer is correct. 22.5 minus 4.3 gives you 18.2. 22.5 plus 4.3 gives you 26.8. So that is correct. All right, next. We have another example. This is one that you can try. It's exactly the same kind of thing as what we were just doing. So again, to find the sample mean, take the average of the upper and lower limits. The average of 20.7 and 25.9 is 23.3. And then to get the error bound for the mean, you take the upper limit minus the sample mean, and that gives you 2.6. All right, so now finding the z-score and computing the error bound for the mean given, let's see, what are we given? I can't see this because there's something in my way. Oh, and I can't seem to, let's see. There we go, given the confidence level. All right, so this is the more typical kind of confidence interval problem. The confidence level, CL, is the area in the middle of the standard normal distribution. So the notation that we usually use for confidence level is 1 minus alpha, which means that alpha is this non-shaded area that's split equally between the two tails. So the combined area of the two white regions is alpha, and the area of the purple region is 1 minus alpha. And of course, when you add those together, you get 1, okay? So if you split that white area into two parts, it has a combined area alpha, which means each separate area is alpha over 2. The z-score that has an area to the right of alpha over 2 is denoted by z sub alpha over 2. So let me just add a label here. So that would be this z-score right here. All right, now fortunately, many confidence intervals use the same values for the confidence level. The most common values tend to be 90, 95, or 99%. And there are a few others. You're going to see them in a chart here. I would like to explain at least one of them. That way, just in case you're given a confidence level that's not one of the more common ones, you'll know how to figure it out. All right, so let me, first of all, get my mouse back. Let's get rid of my scribble here. Okay, all right. So these are some of the most common confidence levels. I mentioned 90, 95, and 99%. They've also thrown in 80% and 98%, okay? So what I would like to show you right now is how to get the one for 95%, okay? So I am going to switch over to, let's see. Give me just a second here. Doesn't seem to want me to switch over. Okay. Okay, here we go. Let's see. All right. This is something I just figured out how to do recently. All right, so I want to show you where the critical z value for the 95% confidence interval comes from. So let's say this is my standard normal distribution, and I'm going to put 95% right in the middle, which means that these two areas combined are equal to 0.05, right? And that means that this one area by itself is half of that. So 0.025, this area is also 0.025, okay? So what I'm trying to find is this z-score. All right. So I'm going to use table A2 for that. Remember that table A2 allows you to find z-scores if you know the area to the left. So if I take this region and this region all put together, that gives me 0.95 plus 0.025 equals 0.975, and I'm going to tack a 0 onto the end of that. And now, if I switch over to table A2, we know that this z-score has to be positive because 97.5% of the area is to the left of it, so it has to be positive. It's much more than half. So here I am on positive z-scores, and right there is 0.9750, and it corresponds to a z-score of 1.96. So that's how they got the 1.96. Switching back to this here. So using the correct notation, that means that z sub 0.025, remember we're talking about z sub alpha over 2. So in this case, alpha over 2 is 0.025. We just found that that z-score is 1.96. So you're going to find it helpful to keep that table handy, the one that you saw on the PowerPoint. Let me switch back to that. Let's see, is this the right one? Yes. Just get back into. All right, there we go. Now, table A2, the table that you have, it does have the critical z-scores for 90%, 95%, and 99%. So if you'd like, but it doesn't have 80% or 98%. So it might be a good idea to actually pick up a pen and just add those two onto the table. I don't think I ever showed you. Just bring the table back. See right here at the bottom, it has those 3 confidence levels and then those 3 critical values. It just doesn't have 80% or 98%. All right. Okay, so here is the formula for how to find the error bound for the mean. So you have to be given the confidence level. And what we're talking about right now is doing this when the population standard deviation is known. It's going to work differently when the population standard deviation is unknown. Okay? So the error bound for the mean is z sub alpha over 2. For example, the 1.96 that we just found, if your confidence level is 95%, times sigma divided by the square root of n. N is your sample size. Okay. All right, so here they're just having me practice using this little chart. This is very easy. Find the z-score that corresponds with a 90% confidence level. So that's right there in the chart, 90% confidence level. The z-score that corresponds with that is 1.645. Normally, when you're using table A2, z-scores are only given to 2 decimal places. So these are given a little bit more accurately. They probably got these values using technology. All right, so yes, 90% confidence level corresponds to alpha equals 0.10, which is alpha over 2, 0.05, and that z-score is 1.645. Similarly, if you need the z-score that corresponds with a 98% confidence level, that's given right here in the table. That z-score is 2.326. All right. Suppose scores on exams in statistics are normally distributed with an unknown population mean and a population standard deviation of 4 points. A random sample of 75 student scores is taken. These gave a sample mean score of 74. And they want me to find the error bound for the mean of the confidence interval with a 95% confidence level. So now we're using the whole formula, z sub alpha over 2 times sigma over the square root of n. Because this is a 95% confidence level, that means z sub alpha over 2 is 1.96. The population standard deviation is given to be 4. The sample size is 75, so we're going to do 1.96 times 4 over the square root of 75, which gives me an error bound of approximately 0.905. Notice that since they only asked for the error bound and they didn't ask for the confidence interval, I'm not using the sample mean. I will use it when they ask for a confidence interval. All right, here's one you can try. Suppose scores in exams in statistics are normally distributed with an unknown population mean and a population standard deviation of 6 points. A random sample of 80 student scores is taken. These gave a sample mean score of 72. Find the error bound of the confidence interval with a 90% confidence level. So using the same formula, z sub alpha over 2 times sigma over the square root of n. 90% confidence level gives me a z-score of 1.645. The population standard deviation is 6. The sample size is 80. That error bound comes out to 1.103. Okay, so now we're working our way up to actually writing the confidence interval. The most complicated part of that is doing the error bound, which we've already done. So once you have the error bound, the way that you get the confidence interval is just add and subtract the error bound to the sample mean. X bar plus or minus the error bound. All right, suppose scores on exams in statistics are normally distributed with an unknown population mean and a population standard deviation of 4 points. I think this is the same example from 2 examples ago. A random sample of 75 student scores is taken. These gave a sample mean score of 74. Calculate and interpret the confidence interval with a 95% confidence level. So we already did the error bound in that previous example. Remember, it came out to 0.905. So now we're going to take that value and add and subtract it onto the sample mean. Remember, subtract it first. So that gives me a confidence interval, 73.095 up to 74.905. So with 95% confidence, we can say that the population mean for statistics test scores is somewhere between 73.095 and 74.905. All right, here's another example. This is, again, recycling that one from, this is now 2 examples ago, again. Suppose scores on exams in statistics are normally distributed with a known population mean and a population standard deviation of 6 points. A random sample of 80 student scores is taken. These gave a sample mean score of 72. Calculate and interpret the confidence interval with a 90% confidence level. So again, we already found the error bound was 1.103. So when we subtract that and then add it onto the sample mean, we get a confidence interval of 70.897 up to 73.103. So with 90% confidence, we can say the population mean for statistics test scores is between 70.897 and 73.103. All right, finally, if you need a specific margin of error, see, the idea here is that the larger sample you take, the smaller your margin of error will be. So let's say that for statistics test scores, I wanted to calculate the population mean with a margin of error of 1 point. I don't want the margin of error to be more than 1 point. So I can use this formula to figure out how big a sample do I need in order to get that desired margin of error. So we take the error-bound formula, z sub alpha over 2 times sigma over the square root of n. And if you use a little bit of pretty simple algebra to solve that formula for n, what you get is this. N equals z squared, this is the same z sub alpha over 2, times sigma squared divided by the square of the desired error bound. Okay, so z squared sigma squared divided by error bound squared. Most of the time, this value of n will not be a whole number, but of course the actual sample size has to be a whole number. Since the calculated value is a lower limit, you always have to round this value up, all right? So for example, if the question was, how many students do I need to sample in order for my margin of error to be 1 point, and n came out to 82.3, what that's technically saying is I need at least 82.3 students. Well, I can't have 82.3 students, and if you do what you normally do with 82.3 and round it down to 82, that's not at least 82.3. So you have to always, always, always round it up. Okay, so the population standard deviation for the age of Foothill College students is 2 years. If we want to be 95% confident that the sample mean age is within 1 year of the true population mean age of Foothill College students, how many randomly selected Foothill College students must be surveyed? Okay, so here's that formula that we were just looking at. We want 95% confidence, which gives me a z-score of 1.96. Oh dear, there is a typo there. Sorry, I didn't notice that. I think the easiest way to fix that is to just change the question. So they're using 3 here for some reason. Sorry, I didn't catch that before. So we'll just pretend that that said 3. I'm the teacher, I get to do that. Okay, all right. So population standard deviation is 3. The desired error bound is 1. So if you crunch all those numbers, 3.84 times 9 divided by 1 comes out to 34.57. So that's saying you need at least 34.57 students. That really means you need at least 35. Okay. Here's another example. A College Board sample estimated the standard deviation of 2016 SAT scores to be 192 points. You are researching the average SAT score. You want to know how many people you should survey if you want to know at a 90% confidence level that the sample mean SAT score is within 40 points of the true mean SAT score. What is the minimum sample size that should be surveyed? So using that same formula, 90% confidence level means Z is 1.645. This time they are using the correct standard deviation. The standard deviation is 192. And we want the margin of error to be no more than 40. So if you crunch those numbers, you get the minimum value of n is 62.346. You may want to round that to 62 because that's what you normally do when your next digit is a 3. Forget about that. Always round it up. Okay. If you need at least 62.3 students, then you really need at least 63 students. And that's the end of confidence intervals with population mean known.